Now we turn to heap sort. It reuses the max heap from chapter 12 to sort a whole array in place. Before we sort, let us recap the one structure heap sort needs. If you have not seen the heaps chapter, this is all you need. A max heap is a complete binary tree packed into a plain array. There are no pointers. From a node at index I, the left child is at 2i plus 1, the right child is at 2i plus 2, and the parent is at I minus 1, divided by 2. Here are the same 6 values drawn as a tree. 16 sits on top, with 14 and 10 as its children, and 8, 7, and 9 below them. The one rule is this: every parent is greater than or equal to both of its children, so the largest value is always at the root, at index 0. That is the fact heap sort uses again and again. Heap sort adds no new sorting logic. It only reuses 2 heap operations. Let us name them. The first is sift down. If a node is smaller than a child, it breaks the rule. We swap it with its larger child and keep going down until it is at least as big as both children, or it reaches the bottom. This costs big O of log n, one path down the tree. The second is build max heap. We call sift down on every node that has a child working bottom up, the last parent first and the root last. This costs big O of n in total. So here is the whole plan. Build the heap once. Then repeatedly swap the root, the largest value, to the back and sift down to restore the rule. That loop is heap sort. We just recapped the max heap. A complete tree in an array whose root is always the largest value. Heap sort applies that repeatedly to sort a whole array in place. First, we build a max heap from the whole array. Build max heap does this in big O of n. Then we repeat one move. Swap the root, which is the current maximum, to the end of the live region. Shrink the heap by 1, then heapify down to restore the heap order at the new root. Every extracted maximum lands in its final sorted slot at the end of the shrinking region. The array sorts itself from the back forward, with no second array needed. Let's read the pseudocode. Heap sort first calls build max heap, which arranges the whole array into a max heap in big O of n, that is the build max heap move we just recapped. Then the loop runs n from n minus 1 down to 1. Each pass swaps A at index 0, the current maximum, with A at index end, its final sorted slot. Then max heapify fixes the new root over the heap that just shrank by 1. Notice there is no new sifting logic at all. Heap sort's whole job is calling those 2 heap routines in the right order. Let's trace heap sort. The whole strip is a live max heap right after build heap. The root at index 0 is the largest value, 16. Each step is one extract. Extract 1. We swap the root 16 with the last live cell and lock it at index 5 in indigo. It is in its final spot for good. Then we reheapify the rest, and 14 rises to the root. The full sift down is chapter 12's job. Extract 2. The new max is 14. We swap it to index 4 and lock it. Then we reheapify the live region and 10 rises to the root. 2 cells are locked at the back now. Extract 3. The max is 10. We swap it to index 3 and lock it, then reheapify. The sorted region grows from the right, largest first. Extract 4. The max is 9. We swap it to index 2 and lock it, then reheapify. Only 2 values are still live. Extract 5. The max is 8. We swap it to index 1 and lock it. Only index 0 is still live. The last value, 7, is the smallest by elimination, so index 0 is done. The array is fully sorted 7, 8, 9, 10, 14, 16. Every extract sent the max to the back and shrank the live heap by 1. Predict, then reveal. After the first extract locks 16 at the back, and heapify down runs on A from 0 to 4, which value rises to the root and gets locked next. Pause and answer. The answer is 14, the largest of the 5 remaining, and the second row locks it at index 4. Each extract sends the current maximum to the back, so an n-element array takes n-1 extract steps, each one a big O of log n heapify down. That is big O of n log n overall. This is heap sort in C. The function takes the array A, and its size n, it sorts the array in place, using the heap we built back in chapter 12. The first line builds a max heap from the array. Now the largest value sits at the root, at index 0. The loop runs in from n-1 down to 1. Each pass places one more value in its final spot. First, we swap the root with the element at index end. The current largest value moves to its final sorted slot at the back of the array. Then we call max heapify on the smaller heap. The heap shrinks by 1, and this fixes the new root so the largest remaining value floats up again. Heap sort's cost is the same in every case. Best, average, and worst are all big O of n log n, that is n extractions, each in big O of log n heapify down. It is not stable because heap reordering has no notion of original order. It is in place, and it has one real downside: poor cache locality, because heap parent and child indices jump around memory, unlike merge sorts and quicksort's mostly sequential access. So watch out for a tempting conclusion. You may think heap sort is the clear winner, big O of n log n guaranteed, and in place, beating both quicksort with its bad worst case and merge sort with its extra memory. But those index jumps scatter memory access, and the poor cache locality usually makes quicksort faster in practice, despite what the theory says.